Okay, so in part 2 of chapter 3, we're going to be taking a look at amino acids, peptides, and proteins, and specifically now we're going to hone in on the ionization behavior of amino acids and peptides, and we're going to start to look at methods to characterize peptides and proteins, which we'll finish up in part 3. So if you think about what we've talked about so far, we have positively and negatively charged R groups, as well as some other classifications that we could use to talk about amino acids. But it's useful, I think, to also think about the fact that there are some uncommon amino acids and proteins. So these are amino acids that are not incorporated by ribosomes, with the exception of selenocysteine. And these are amino acids that arise by post-translational modifications of proteins. So that's after translation, we make a change to the structure, and that's how these amino acids result. So they're what we think of as reversible modification. So especially when we're thinking about phosphorylation, these could be really important in terms of regulation and signaling. And so if we're thinking about structures of side chains of our 20 naturally occurring amino acids, we should, at this point, be pretty comfortable with their names and codes, both the 3-letter abbreviation and the single-letter abbreviation. So if we take a look at these modified amino acids, so here are some examples. We've got hydroxyproline, 5-hydroxylysine, 6N-methylysine, and gamma-carboxyglutamate. And if we think about this gamma-carboxyglutamate, this is a molecule that has the ability to coordinate calcium, and it's also not uncommon to see other examples, say for example like our selenocysteine and then the desmosine. And these are all examples of perhaps less common amino acids, but still molecules that do significant work within living organisms. So how do these come about? Well, we're really looking at reversible modifications. So here are some other examples of where we might see changes that result in a slightly different amino acid. So the addition of a phosphate, you can see here the methylation of an amino acid, or forming the acetyl group, forming an ester, and then sometimes actually the addition of an entire other functional group and moiety off of an amino acid. So while we've talked about the 20 naturally occurring amino acids, it's also really useful for us to think about the fact that we're going to potentially see other types of molecules based on reversible modification. So we're going to hone in today talking about the ionization of amino acids. So when I'm in an acidic environment, so when my pH is low, the carboxyl group is going to be protonated. That means it keeps its hydrogen. And when I think about that, that means that likely my amino acid is going to be in a cationic form because that amino group has a positive charge. At a neutral pH, say pH 7, that carboxyl group, though, becomes deprotonated. It loses the hydrogen, but the amino group stays protonated. So because I now have a negative charge on the carboxyl group and a positive charge on the amino group, this is what we refer to as a Zwitter ion because it has a net charge of 0. However, if I go towards alkaline pH, now my amino group is neutral. I've lost that proton, so I've lost the positive charge, and the carboxylic acid is still in an anionic form, so I now have an overall negative charge. If you think about that in terms of the molecules that we regularly encounter, let's say, for example, taking a look at glycine. So here's glycine, right, where everything is protonated. The carboxylic acid is protonated, the amino group is protonated, and so the overall charge is going to be a positive. If you note here, right, this is when my pH is low. As my pH increases, right, I cross through my first pK. So my pK1 is 2.34. And this, right, is where I have half of my COOH protonated and half deprotonated. Once I reach my isoelectric point, that negative charge now predominates. And so most of my carboxylic acid is actually the carboxylate, right, or the negative charge. And it's because I have this negative charge and a positive charge that I now have the Zwitter ion. So that's where my net charge, right, is neutral. And that requires one full equivalent of base in order to do so, because I have to completely deprotonate this proton. Now, if I were to continue adding base, if I were to go all the way out to 2 equivalents of base, I would cross through my second pK. This is 9.6. At this point, I would be deprotonating this hydrogen. So it becomes the amino group, and now my overall charge is a net negative. You need to be comfortable drawing both the molecules themselves and labeling their respective pKs, as well as their isoelectric point, on a graph that looks like this. Now let's think about why we might care about this content. Well, we know the chemical environment affects our pKa values. So our carboxy group is going to be much more acidic than in carboxylic acids, or an alpha amino group is going to be slightly less basic than in amines. And so if you take a look at what's going to happen from a behavior standpoint, so let's say I have my alpha amino acid glycine. Its pKa is 2.34. Its oppositely charged groups lower the pKa because it stabilizes that Zwitter ion. Notice, right, this Zwitter ion is the most predominant form in terms of the vast range of pH that we see. It's really only when it's a low pH that we see this form, or when it's a very high pH that we see this form. Now in this form, our electronegative oxygen atoms, right, pull electrons away from the amino group and lower its pKa. Likewise, if we were to have, say for example, a methyl substituted carboxyl and amino groups, we would actually see a slight shift, right, where methylamine, the normal pKa for the amino group, is about 10.6, whereas the normal pKa for our carboxyl group is about 4.8. So it's useful to think about how the environment that an amino acid is in will impact its behavior. Part of the reason why we look at the pH and the interaction of these amino acids is because we understand that they can function as buffers. So amino acids with uncharged side chains, such as glycine, have 2 pKa values. The pKa of the carboxyl group is typically 2.34. The pKa of the amino group is 9.6. So it can act as a buffer in 2 pH regions. So let's take a look at how that would occur. So if we go back here to glycine, right, there is a proton that can easily be removed here, as well as a proton that can easily be removed here. Notice where the slope of the line diminishes. This is our buffer region. And so what we're looking for is what's going to be the behavior of our molecule. So if we take a look here, we know that Zwitter ions are the predominant at pH values between our pKa values of the amino and the carboxyl groups. So for any amino acids without ionizable side chains, so without R groups that can change their charge, the isoelectric point, or the equivalence point, Pi, is simply the sum of the 2 pKs divided by 2. And at this point, we know that our net charge is 0. Now, what are the criteria, or what are the behaviors of these amino acids? Well, they're going to be the least soluble in water, and it's not going to migrate in an electric field when that net charge is 0. So it does change the behavior of that molecule. Now, if we look at ionizable side chains and the way that they show up in titration curves, you could also titrate for an ionizable side chain, but our titration curve is going to be a little bit more complex. In fact, our pKa values are going to be discernible if those values are more than 2 units apart. So why then would side chain pKas be so much higher? Well, let's take a look. Here is histidine with its respective charges. You'll need to be able to identify both what stays protonated at low pH, what loses its proton at a slightly higher pH, and then, right, what the Zwitter ion looks like, and finally, right, what the fully deprotonated form of the molecule looks like. So in this case, if we're looking here, right? The very first proton that leaves is this carboxylic acid proton to become our negative charge. Then the next proton to leave is the proton on the side chain, on the histidine itself. Notice here I have a significant change in terms of my charge because I lose a proton, so now instead of having an overall charge of 2, I become an overall charge of +1. Here, once I lose this proton, I become an overall charge of 0. And once I lose my final proton off of my amino group, I now have an overall negative charge. Now, if you take a look at these respective pKa's, I have a pKa of 1.82, pKa of 6.0, and a pKa of 9.17. Now, where is the isoelectric point? Where is my Zwitter where the charges sum to 0? Well, its pi, or the isoelectric point, is at 7.59. So when my side chain is ionizable then, I need to be able to identify the species that carries a net 0 charge. I need to be able to determine the pKa value that actually determines the strength of this Zwitter ion. That's always going to be my pK2. And I also have to be able to determine the pKa value that defines the base strength of this Zwitter ion. That's pK1. And then you're going to take the average of those two pKa values. So what is the pi of histidine? You would do that calculation by taking our pK1, which is 1.82, our pK2, which is 9.17, divide them by 2, and that gives you your isoelectric point of 7.59. Now, when we think about how these amino acids form peptides, it's useful for us to think about the formation of a covalent bond as the loss of water. So if we're going to form the bond, we're going to lose water. That's going to occur through a condensation reaction. If we're going to break the bond, we're going to add water, and that's going to occur through a hydrolysis reaction. Now, peptides themselves are very small compared to proteins. Our molecular weight is going to be less than 10 kilodaltons. The peptide ends are not the same. So we always start our numbering and naming from the amino terminal end. Right, so this is what we refer to as the amino terminus, and this is the carboxy terminus. Notice the pattern that we observe here. It's NCCN. NCCN. On repeat, because each of these are units, right, of amino acids. So there's 5 amino acids that comprise this short peptide. Next, we're going to be talking about the way that we can isolate or separate peptides and proteins based on the structural features of amino acids. Thanks again.